Hello students, in this series of design of built up section, this is my fourth video. This is my fourth video. So if you watch my second video, that is design of built up section, where I have solved a problem, design a raised column 10.5 meters long to carry a factored load of 1000 kilonewton. The column is restrained to position but not in rotation at both ends. Use two channel sections placed on back to back. So in this particular video, design of built-up compression member, the complete laced design was not done. The problem was solved only for the design of built-up members. So the design was, we have selected two channel sections. If you watch that video completely, you will find I have stopped my video on that day in that video by selecting two ISMC channels. By selecting two ISMC channels at a spacing of 184 mm. So the continuation of that part, the design, because the problem is involving laced column. So design of lace system, I am continuing in this part of my video. So in this, prior to this video, I have released one more video, that is design of lacing system 1. In that, I have given all the design steps. So if you have seen that video, solving the problem becomes very easy. In this video, I am taking the same steps and I am continuing the design. So if you want to understand the complete problem of the design of a laced built-up section, then you have to watch my first video with the name or with the title Design of Built-up Compression Member. Built up compression member. Then design of built up compression member 1. Then third part, design of lacing system 1. And this video, design of lacing system 1, in which I have given all the design steps, 12 design steps, explaining each and every step I have explained in this video. Design of lacing system 1. Then this is my fourth and last in the series in the design of laced built up columns or laced built up compression member. So this is my last video with the title Design of Lacing System 2. So all these four videos, if you watch, you will get a clear idea to design the built up section, checking the provisions from IS 800. When you design a structure, steel member, all the provisions, all the requirements, all the limitations given by, suggested by, recommended by IS 800 must be satisfied. So you watch all these four videos to have a complete in-depth understanding of the design of built-up compression member. Now coming to the design of lacing system, that is the problem which I have solved in this. I'll continue with that problem, the design of lacing system. So as you know, the first step is, I can write it, this is the continuation of my previous video. Fine. So whatever section you have selected, like this was to ISMC, they were the one which we have designed were to ISMC. Yes, ISMC 250. ISMC 250 with a spacing of 184 mm, with a spacing of 184 mm. Oh, sorry, it is ISMC 300. ISMC 250 failed, so we designed it for ISMC 300. Fine. So ISMC 300 with the spacing back to back, they were placed back to back. The spacing between those two sections, we got it as 184 mm. Yes, 184 mm. So this was the design which we have done in the last video. Section was ISMC 300. Now in this video, we are designing the lacing system. Following the steps given in the video 3. Fine. So the first step was to select the lacing system. Choose the lacing system, whether you want to go for single or double. That system you have to select along with the angle of inclination. So let us select first, let us try the single. If it is failing single, then we will go for double. So let us try single lacing system. Single lacing system. Okay. Then also we have to assume the inclination. So as I suggested in my earlier video, you have to go an angle between 40 and 45 so that you have a maximum efficiency in the connection. So assume or assuming the inclination theta of lacing bar, let us go for 45 degree because tan 45 will be easy to do. Fine. So that's our step 1 completed. If you follow the step, within no time you can complete the design of lacing system. So my step 2 was find the gauge distance. Find the gauge distance and A, distance between the center to center bolt. So find gauge distance. So and A. A is the distance between the bolt centers. So to understand this, you can see this is your center line of the compression member. You'll have a bolt here. You may have a bolt here, depends. Then this is your another channel section ISMC 300. You'll have a bolt here. Fine, right? So G is the distance between center line to the edge of the channel section. So we can assume it as 50 mm. This is 184 from the design. This was our spacing. Okay. So this is 50 and this is 50. And the distance between center to center of the bolt line is represented by E. Fine. So we can say, we can provide G value like 30, 40, 50. Provide G is equal to 50 mm. Then we will get the distance A as 2G plus S. So 2 into 50 plus 184. So you get the distance between the bolt centers, 284 mm. Okay. So second step is also complete. Fine. So let us go to the next step. Step 3. Step 3, find the length between two lacings. Find length, capital L, between two lacings, two consecutive lacings, I should say. Okay. So let us work out on the same diagram. Okay. If I take the lacing, this is one lace and the other will be this lace. So this is L. Okay. So as discussed in the previous video, if it's a single lacing, L is given by the formula L is equal to 2A by tan theta. Okay, so 2 into 284 by 1045 degree, which is 1. So we got this as 568 mm. So this is also completed design of length between the two lacing bars. Also, along with this, we have said, or in my steps video you have seen, we also have to find length of the lacing bar. Okay, length represented by small l of lacing bar. So the formula for that was a by sine theta. L is equal to a by sine theta. Okay, so A is 284 mm. Just now we have calculated. Sine is 45 degree. So on solving, we get L, that is length of lacing bar, as 401.636 mm or 64 mm. You can round it up to that value. Okay, so this is also completed. Length of lacing flat or lacing bar. Step 3 is complete. Going to the step 4. So watching my previous video will be very helpful in solving this problem. Time will be reduced for solving once you remember the steps. So step 4 was finding the slenderness ratio. Slenderness ratio. So all of you know the formula for slenderness ratio is the length between the two lacing bars by R minimum. R minimum. Okay, so R minimum for the problem which we have said solved ISMC 300 section. If you want, you can refer. It is 21.76. It was RY. So 21.7, sorry, 26.1. R minimum for ISMC 300 is 26.1 mm, which we found it in the first part of this problem. Okay, so this has come to be like L, we got it as 568, and this R minimum is 26.1. So on solving, we get this as 21.76 mm. As per IS 800, it shall be less than 50. Yes, okay. It shall be less than 0.7 times the maximum slenderness ratio. Okay. Once again, if we refer this design of ISMC 300 built-up column, we had maximum slenderness ratio as 93.5. So these values are obtained from the video posted on 20th September with the title Design of Built-up Compression Member 1. So this we got it as 65.45. So it's less than 21.76 is less than 50 as well as less than this. So okay, the slenderness ratio is acceptable. Okay, so step 4 is completed. Now coming to step 5. Step 5 is find the effective length of the lacing. So effective length of the lacing is equal to the length, because it is a single lacing system. The two bolted single lacing system. So it is whatever length we got it, that itself is a effective length. That is 401.63 mm, which you got it in step 3. Okay. Fine. Step 5 is also over. Now step 6. Select thickness. T of lacing flats, or you can say system, whatever you are selecting. Okay, for this, as per IS 800, thickness shall be more than effective length by 40. Okay, you can see 7.6.3. Thickness shall be more than 1/40th of its effective length for single lacing. So I'll just find out how much is it shall be more than effective length by 40 for single lacing. So let us see how much is effective length. 401 401.63 by 40. It is coming to be 10.04 mm. So our thickness shall be more than 10.04. Minimum is 10.04. So you can adopt as per your convenience. You can adopt more than what you got it. So adopt, or you can say provide. Anything you can say. Adopt T as 12 mm. The thickness of the flat plate is 12 mm. Fine. Now coming to the B. So width of flat. So as per IS 800 provisions, width shall be, you can see, the minimum width of the lacing bar shall be 3 times the nominal diameter of bolt. So it's 3 times. Anyhow, we haven't selected the three bolt diameter. So let us provide, if if it is not fulfilling the passing the test, then we can revise it. But to begin with, we can provide 50 mm wide flat. So the flat which you are using as lacing, flat plates you are using, so its width is 50 mm and thickness is 12 mm. Okay, so finally what we are selecting, we are writing provide a flat section, like ISMB, Indian Standard Beam, medium weight beam. Similarly, flat sections will be represented in this fashion. Width you have to write, then Indian Standard flat, and then thickness. So this is the section which you are selecting for your lacing. So it means it is 50 mm wide and 12 mm thick. So this is how we notate, or we give notation for the plates, flats. Okay. So the step 6 is completed with the design of the flats. That is, we have arrived at the width as well as at the thickness. Now coming to next step, step 7, maximum slenderness ratio of the lacing system. Okay, so your say lacing system is no, it's not angles, it's not it's not tubes, it is flats. Okay, so we are finding out the slenderness ratio of the lacing using the formula given in the code, that is effective length into root 12 by T. So effective length was 401.63 into root 12. By coincidence, thickness is also 12. So on solving this, we got the slenderness ratio value for lacing as 115.945. If you see the design steps video, then you will find that it should be less than 145 from the IS 800 provision. So we have satisfied IS F50 mm wide, 12 mm thick is okay. We can go for it. Fine. Now in step 8, we have to find out the compressive strength of flat plate. We have to calculate compressive strength of the flat plate which you have selected, that is ISF 12 mm thick, 50 mm wide. Okay, so that we get design strength. So it's PD is equal to area of flat plate multiplied by FCD. Okay, so this is 50 by 12 node. Okay, so this is the design compressive strength which we have obtained, we will get using buckling curves. Okay, using buckling curve. So for buckling curves, we should have the ratio KL by R, that is lambda, for lambda 115.94 and grade of steel 250. Refer the curve C, buckling curve C, come from curve C. IS 800 curve C. So it is in the beginning. All buckling curves are in the beginning. Curve 11, 15. Just let us check out once. Yes, this is design compressive stress FCD. Okay, this is for class. No, for curve C we have to go for curve C. Okay, here. So you can go 250. This one in this 250 and KL by R was 115.94. So something between this 94.6 and 83.7. In between these two, if you interpolate, because our lambda value is 115.94. So it will lie in between these two. So after interpolation, we get the value of FCD. So it is from buckling curve 9C. So from buckling curve 9C, I'll write it here, 9C. If you interpolate it, you'll get the value of FCD. From curve C, after interpolating, the values, okay, we get FCD as 88.37 Newton per mm square. So this you have to substitute in the PCD, sorry, design strength of the lacing bars. So area was 50 by 12 and stress is 88.37. Now if you divide it with 10 to the power of 3, you get the answer in kilonewtons. Okay, so we got this as 53.02 kilonewton. This is the design strength of lacing bar. So this completes our step 8. Step 9. Calculate transverse shear. Calculate transverse shear. It's given as 2.5% of the axial load. So axial load is given in the question. That is, it has to carry 1000 kilonewton. Okay, that was, if you watch my previous video, you will come to know this. This is the axial load given. So this comes out to be 25 kilonewton. Fine. This is the transverse shear. So once you find out the transverse shear, this is in two panels. Whatever you get transverse shear, it will be in two panels. 1 minute. Once again, I have to draw the figure like this. Single line diagram. I'm just showing. So this is one lacing. This is another lacing. So the shear you are getting is in two lacings. Okay. So two lacings. So we want in each transverse shear in each lace. So transverse shear in each, you can say panel or you can say flat, whatever you want you can see. So that will be equal to whatever V you got it divided by number of laces. That is 25 kilonewton you got it by 2. So it's 12.5 kilonewtons of transverse shear is coming in each lace. So if I take this one, then transverse shear coming is 12.5 in each. Then from this, I have to find out the force in this. If I have to find out. Okay. So in the same step, we have to find out the compressive force. You see the notation how I have done. So compressive force in the same lacing. We got transverse shear in the lacing, and now we are finding out compressive force in lacing bar F, because of the shear what you are getting. So this is equal to whatever you got V by N. You can see this is its component. Okay, V by N into 1 by sine theta, or I can say whatever you got it. Suppose this is 12.5. We want its inclined component. So this is opposite, this is hypotenuse. Okay. So for example, this is V by N, this is F. Then V by N by F is equal to sine theta, or F is equal to V by N by sine theta. I hope you got it. Okay. So that I am doing it. F is equal to 12.5 V by N by sine theta. I can write it like this. Fine. So 12.5 is V by N, but theta is 45 degree. So sine 45. So we got the compressive force in the lacing as 17.68 kilonewton. Step 9 is also completed. Step 10 is the check for compressive stresses. See, step 10. I can say check for compressive and tensile forces, you can say, or stresses, you can say. Force multiplied by area, sorry, stress multiplied by the area will give you the force, right? So, we already know the design strength of the lacing is 53.02 kilonewton, which we found in step 8. Already we have found the compressive stress of 88.4 in step 8. Okay. Now this shall be more than F, compressive force in the lacing bars. So the bar can carry 53.02, but coming on the member is 17.68. Fine. So therefore it is safe. Safe in compression. That is, it is safe with respect to compressive stresses. Now we have to see the safety with respect to tensile stresses. Okay. So this is with respect to compressive stress completed. Now with respect to tensile stress. Check for tensile strength. So how do you get tensile strength? In design of tension members, you have seen we will find out cross section yielding and cross section yielding of plates and tensile strength of tension members. So we have tension strength as tension strength. I can say it as mm, tensile strength. Tensile strength of plates. If you refer tension design of tension members, you have a formula 0.9 into B minus diameter of hole. B is the width of plate and this is diameter of hole into thickness into the ultimate strength of bolt by gamma M1. Fine. So with this you get the tensile strength of plate. So 0.9 into 50 minus, if you use 16 diameter bolts, the diameter of hole will be 16 plus 2. So 18. It's DH. D suffix H. It's not D into H. Okay. Into thickness of plate was 12 mm. The ultimate strength is 410. Ultimate stress gamma M1 is 1.25. Now, if you divide it by 1000, you get the answer in kilonewton. Okay, so that is 113.35 kilonewton. This is the tensile strength TDN, net tensile strength. Then you have gross section yielding, TDG. We can write this as TDN if you want. Then TDG. TDG is equal to AG into Fy by gamma M0. So gross area of plate is 50 by 12. Yield strength is 250. Okay. By partial safety factor is 1.10. Again, if we divide it with 10 to the power of minus 3, we will get the cross section yielding strength of the flats which we are using as lacing system. So this is the values. So least of these two, whichever is least, that will be the tensile strength of the lacing bars. Tensile strength of the lacing bar. Since it is a plate, lacing bar is a plate, it's a flat. So we are using the tension member formulas. Okay. So least of TDN and TDG is design tensile strength. Tensile strength of the lacing flat. Lacing flat. Okay. So that is design tensile strength is 113.35, the first one. TDN is our design. So this is your. Again, this is more than F. Again, we have to check it with F, that is 17.68. So both the cases it is passing the test. Therefore, it is safe. So we have completed the design of lacing system. Right? Number of bolts, all this. If you want, you can calculate. Our next step was step 11, number of bolts. Step 11, number of bolts. Number of bolts. Okay, that is the connection design. Step 11 was design of connections. Okay, so assuming that 116 mm diameter bolt is using in each end, like here one and here one. So one bolt is coming for each lacing. Okay, assuming one 16 diameter bolt is used to connect both the lacing flats. Like one is going this side, okay, one is coming here. Fine. So we are using one bolt of 16 diameter. Fine. So the shear plane falls. We have to find out the strength of bolt in double shear because one plane is coming this side, one is coming. So we have to find out strength of bolt in double shear. This is the design of connection. Strength of bolt in double shear is equal to 2 into net area of bolt into the ultimate stress in the bolt material by root 3. In connections, we have seen these formulas, gamma material of bolt. Okay, so substitute that. Net area of the bolt will be 0.75 times the diameter. You can calculate it and keep it aside. Net area of bolt will be 0.75 times the diameter of bolt. Diameter of the bolt. So that you are getting it as 2 into 157. FAB is 400 standard value by root 3. Partial safety factor is 1.25. Okay, if you divide it by 1000, you get the value, that is the strength of bolt in double shear, 58.01 kilo. Then strength of bolt in bearing. You have to find bolt value. So least of these will be the bolt value. Strength of bolt in bearing is given as 2.5 kb into d into t into fu by gamma mb. Okay, so 2.5 kb is 116 is the diameter of bolt. Thickness of flat plate is 12 and fu is 410. It's not fub, it's fu 410 and 1.25 is the partial safety factor divided by 1000. You get the strength of bolt in bearing. This was strength of bolt in shear. Okay, so this is coming out to be 157.44. This kb value is 1. We have just taken it from our previous calculations. Okay, so out of these two, whichever is least, that is the strength of bolt. Hence, strength of bolt is whichever is less. One is 58, another is 157. So 58.01 kilo. So once you get it, you can calculate the number of bolts required, right? So force on bolt, we have to first find out force on bolt. This is the design of connection. Force, what force is coming, how much force is coming on the bolt from the lacing flat. To understand this, again I will draw a simple figure and then I will explain. 2 into Vt, that is on single plate you got it now, that divided by, okay, that is V by N, I can say transverse shear by N, that is 13.5 what you got it, then this divided by tan theta. So you can have again same geometry, you have to see it. This is your bolt, okay. So this will be the transverse shear coming on it. Another plate will be coming like this. So there are two. So it's 2. Find tan theta V by N is the one which I have shown here. Yes, you can see this is V by N. Okay. V by N by tan theta. That is from the simple geometry of the connections you will get it. If you go through this, this is V by N by cos theta, that is equal to V by N is 13.5. In each panel we got it 13.5 kilonewton divided by tan 45. That is 1. Fine. So again we got this as 27 kilonewton is the force on bolt. Okay. So once we get this, we get number of bolts. Number of bolts required will be equal to the force on each bolt 27 divided by the strength, least strength, that is strength of bolt 58.01. So we are getting it as 0.465, which we cannot use, so we should minimum have one bolt. So provide 16 mm dia, one bolt, okay, of grade, because you are designing the connections, so we have to complete the statement. Provide 16 mm dia, one bolt of grade 4.6 for making the end connection. So this finishes for making end connection. Okay. So this is how you have completed the design of lacing system. Design of lacing system will be incorporated in the same question of design of built-up section. So design of built-up section includes the design of batting, because when you take two sections, whether it can be channel, angle, 4 angle sections, I'm showing you here. Okay, 4 angle sections. So whatever you take, you have to use the connectivity. You have to connect them. Then only it will become a single section. Otherwise, 4 different points. So this connectivity is the lacing system. How to design it, we have seen in this video. So you have to follow all the 12 steps. Then you will end up the design of lacing system. Give your valuable comments on this video. Any improvements required, you can post it in the comments. Valuable comments are always welcome. Bye everyone.